Okay, hello everybody. So in today's thing, we'll start a new topic called time response analysis of systems. So far what we have learnt is, given a system, how would you model that? Model that using basic conservation laws, from voltage laws to current laws, laws of force and so on. And from that we could derive models based on transfer functions. If we have systems which are interconnected transfer functions, then we had techniques of how to get the overall transfer function via block diagram reduction or the signal flow graph techniques. Okay, so what we will learn today is, once I have a model, so what could I do with the model, or how does the model behave? So the first thing is, after I obtain the model, how to know the performance of a control system for any input signal, and next is how to design a system which meets some desired response, but it could just be some natural response or even to fit a control requirement. Okay, so how do we visualize this? So given a system or given a model, so let me say when we are subject to driver's license test, right? So the driving inspector doesn't really test us for all possible conditions on the road, which could include high speeds on freeways, it could include heavy traffic on the city lanes, it could involve chaotic traffic with buffaloes running around, kids playing cricket on streets. We don't get tested for all those things, right? So instead what the driving test does is, under standard Indian conditions, so you'll just have a little predefined track which you have to drive to pass your learner's test. In that track, okay, you have several things, right? You have to go straight, you have to take a sharp turn, you have to make a pitch figure of 8, you have to take a reverse, you have to park, and several other things. So these are the standard things which we will encounter while we drive on roads, right? In a similar way, if I am being interviewed for software engineer, right? So I go as a model, my model could be my BTech degree with a CGPA of 8.65 with a several list of courses. Now I want to hire you as a C programmer, right? So I will not give you a real time project to work on immediately, right? Or I would also want to test how would you react or how would your performance be on a certain project or a certain deliverable. Then I would ask you some basic questions on sorting algorithms. It could be things related to pointers, linked lists, some functions, interconnection with the database and so on. And based on all these things, I will get an estimate of how your performance could be while handling a real time project. Now this could differ from person to person, right? Either you could be a fast programmer, right? You could write a program or code very fast. You could, some other person could take a longer time but write a code which is more efficient. So all these I would get to know with some basic standard test signals. Similarly, what will happen is, when we design a control system or we analyze a control system or a model, we will subject it to some standard text signals, because we would not be able to emulate a real time control input kind of signal. Okay? So these test signals will tell me how my system will react under changing conditions. The conditions for a system could be, well, I have kind of a shock which could be an impulse, I could have a time varying signal which could be modeled as a ramp signal, I could have just a sudden disturbance which could be tested with a step signal, and so on. So throughout this we will see how my system would behave. System could be of different nature, right? So how my system would behave based on certain standard test signals. Okay? And this will broadly constitute the entire time domain analysis and design specifications. Okay. So the time domain analysis refers to analysis of the system performance in time, that is, how my system variables, particularly the output, will vary with time, right? So how long does it take for a signal to reach a certain value which I want, like a speed of a car. You say Whenever you see this car related programs in these news channels, usually they come on Sunday morning, you say, oh, this Audi A4 or A6, they go from 0 to 100 in 5 seconds, somebody goes in 6 seconds. My own little car would take about 30 or 40 seconds, right? Sometimes it possibly would never reach. Okay. So, what describes the evolution of the system variables? Okay. So, in standard terms, there could be two kinds of response, right? The natural response and forced response, also classified as the transient response and the steady state response. So, I will shortly define what these things mean. But in both cases, the complete response is given by combination of both the natural response and the forced response, as well as the transient and the steady state response, right. Okay. So, what is a natural response? It also is referred to as a zero input response, which means the system's response to a certain initial conditions with all external forces set to 0. So, if I take a simple RLC circuit, this would be the response of the circuit with initial conditions. The inductor could have some initial current, or a capacitor could have certain voltage with all independent voltage and current sources set to 0, which means there will be no external sources. Say for example, I have a capacitor and I have a R, a C with some initial charge I would call Q0. The natural response would be that the charge, if I plot with time or possibly even the current, that entire charge gets dissipated through heat energy in this resistance, right. That is the natural response. I could then add further elements, an inductor with initial charge and so on. Okay. The forced response is the system's response to external forces, again assuming that all initial conditions are 0. So, again if I look at this circuit and I add a voltage source here together with a resistance, it will have a different kind of response. Okay. We will shortly see what these kind of systems mean and how these kind of responses would look like. Okay. So, here there is this external voltage source, here there is no external voltage source, right. So, that is a little distinction between the natural response and the forced response. It is also called the zero state response. Okay. Similarly, I have two classifications in terms of the transient response. So, all this analysis, when I make this further statements, I would be referring to systems which are stable, right, and I will define formally what is stability a little later, but for the understanding of this particular module, it is sufficient to know the following definition, that stability means, so if I am at an equilibrium position, take my pendulum is just at this equilibrium position, if I perturb it slightly or I start from this initial condition, it will eventually come back to this its natural state or the equilibrium position. So, all systems which are subject to some external perturbation, which then retain their original configuration, would be called as stable systems. That definition is enough for now, right. You can think of it again as simple as the example of a pendulum, right. If just somebody comes and just pushes this, it just goes back to the equilibrium position. Same like an alarm clock which wakes you up in the morning, right. So, your natural equilibrium position is the sleeping position, and if you have your alarm clock waking you up, there is a little disturbance or a little shock, and then you switch off the alarm, put it to snooze and then go back to sleep, which means your stable equilibrium position, which is sleeping position, is always stable, right. Okay. So, we will talk of those kind of systems. So, in this context, the transient response is the response that goes to 0, or this response vanishes as the time tends to be large. So, we will shortly see an example with this. It could also be written, or it could be tied to any events that affects the equilibrium, right. So, as I said in the case of this pendulum, right, that the response, it just vanishes as time goes to a very large value. Steady state response, well, this is the response of the system after all the transients have died down, right, or as time goes to infinity. Again, we will see this with help of example. So, total response of any system would have two components, the transient response and the steady state response, and steady state response could also be just the 0 thing itself, right. Okay. Now, as I said earlier that we will, or based on this nature of responses, we will subject our system or the models which we have or even the control system to some standard test signals, right. So, these standard test signals would be a unit impulse, which could be just a shock, a unit step, which could be just a sudden change in the system. For example, if I have 10 people in my room with my air conditioner set to 24 degrees, 10 more people add up to the room and just stay there, that is a sudden change, right. It is like a step disturbance. My occupancy is going from 10 people all of a sudden to 20 people, or a ramp or a constant velocity where one person is being added every minute, or parabolic, right, which has like kind of a units of, or you can visualize it as something moving with a constant acceleration. And of course, you can have periodic signals, like for example sinusoidal signals. So, for the moment we will analyze impulse, step, ramp and parabolic signals, and postpone the sinusoidal analysis when we will do the frequency domain analysis. Again, these inputs are chosen because they capture many of the possible variations that can happen in a real time scenario, right, as the driving example or even the C programming example, right. And then the design specifications could also be based on the response of my signal to a certain inputs. Okay. So, just to recall how these signals look like, well, a unit impulse, as we saw in our earlier lectures, is just signal for which I integrate from infinity to infinity, the area goes to 1 and it just looks something like this, right. Similarly, step is a signal that switches to 1. So, just at t equal to 0 plus I am at 1 and then I just stay at 1, and for all t less than 0 I am just at 0, right. So, the Laplace transform we know of an impulse is 1 and of a step I know it is 1 over s. Ramp is something which is just with constantly increasing with time at maybe a slope of 1, or it could also be have a different slope depending on what is the value of this a, and then the Laplace transform of this would be a over s square. Okay. Similarly, with the parabola, right. So, you have a t square by 2 and then the response increases actually faster than what it was here. So, one thing which you could notice is I take this parabola a t square by 2 and I differentiate it, what I get is a t. Okay. Similarly, I differentiate, so this is the parabola, I differentiate it to get a ramp, right, that is, you can see it here. Now, I differentiate a ramp and I get a step, right. Okay. Now, just keep this in mind for a while, that I differentiate a parabolic signal to get a ramp, I differentiate a ramp and I just end up with a step. This is a step of size a. Now, we will see, does the response also have certain behavior like this, right. We will just see if that is true or not. Okay. So, the simplest of all systems are systems with only one pole and are called first system. There could be some simpler systems where I just go from here to here, there is just a number 1 and I am not worried about anything, right. So, those are not of interest. There is some dynamics here, right, in terms of tau times s. So, if I just do the standard feedback interconnection, I compute the transfer function, I just get that the transfer function from r to y is y over r is 1 over tau s plus 1, and usually r could be the reference signal which my system is subject to, and I will see how my system behaves for different reference signals, right. The tau is a system constant and it characterizes the speed of the response of a system to an input, and we will see this with the help of an example. So, let us just start with dealing with first order transfer functions which look like this, 1 over tau s plus 1. Okay. So, if I just take the impulse response, now we will use all the tricks which we learnt in Laplace transform, solving of differential equations and so on. So, my input or the reference is just 1, y of s, which is the transfer function g times r, looks like this. Y of t, I just take the inverse Laplace of this guy and I get this guy, right. So, 1 over tau e power minus t over tau, where tau is the time constant of the system. Okay. So, if I just look at the plots quickly, right. So, if I choose a particular value tau equal to 1, then my response just dies this way. For tau equal to 2, I have something like this. Okay. So, you can see that with changing time constants, your response also changes. For example, the blue line, which has a smaller time constants, approaches the horizontal line faster than the black line, which has a higher time constant. Okay. How does it look in terms of the steady state and the transient response? So, this guy 1 over tau e power minus t over tau is called the transient term. If you see that how did we define the transient term, that these guys tend to vanish as time becomes very large, right. So, as time t goes to infinity, this guy goes to 0, and of course, the steady state term here is just 0, right. As I said earlier, the steady state term, that the y eventually, so what the term or the value which the transient term settles down could actually be the steady state value, which is true in this case. Okay. Now, I go slightly further, right. I look at the step response, or more simply a unit step. I can change the magnitude, but nothing much changes in the analysis. So, y of s is again the transfer function is just a first order transfer function, the reference is a step. So, my overall output would look like this. Okay. And then I do some tricks here and get the inverse Laplace transform as 1 minus e power minus t over tau. It is something different here than what we had learned earlier. If I just plot this for two values, say at tau equal to 1, I start at 0 and I go and I end up at 1 asymptotically or eventually. I take tau equal to 2, I still end up at y equal to 1, but a little slower than before, right. Okay. So, in this case there are like two terms, right. So, this is the term which vanishes at infinity, right, that the transient term, and this is the steady state term, right. At steady state what remains is only this guy 1, and at steady state, if I just write that down, y of t limit t going to infinity is 1. Okay. So, I could also compute it directly from here, right, just to see how the steady state looks like. I can just use the final value theorem, right, which goes limit s tending to 0, s times y of s is limit s going to 0, s times 1 over s, tau s plus 1, these guys vanish and I am just left with 1. That also is in agreement with what I get here, and the system is stable. So, I can always use the final value theorem, right. So, I have a transient term I can see very explicitly, and a steady state term which is actually non-zero. In the previous case, the entire response was just going to 0. Okay. Now, something good happens here, right. So, look at this signal, right. So, what I have is that y of t is 1 minus e power minus t over tau, okay, and say t equal to 0, y of 0 is 0, and that is what even the plot says. Okay. And at t equal to the value of the time constant, I have y of t is 1 minus e power minus tau over tau. So, I am just looking at 1 over e power minus 1 is like 0.632 or 63.2% of the final value. Okay, right. So, what I could observe here is, okay, let us say what happens even at t equal to 2 times tau, I reach, so my y of t would be 86.5% of the final value. I do it for 3 tau, so y of t at this, for this t would be about 95%, and at 4 times the time constant I have y of t is like 98.2% of the steady state value, which is 1, right. Okay. So, I can just plot this here that at t equal to 1, I can just, so for the blue line this will work nicely here. So, I will just be somewhere, so this is like the 0.632. Okay, so few things to observe here, right. So one is, okay, let us see what decides this, if who goes fast and who goes slow. Okay. So let us try to differentiate this signal, right. So I have d over dt of y of t, that is so I have 1 over tau e power minus t by tau. Okay. Now at t equal to 0, so d over dt of y of t is 1 over t. Okay. So the initial velocity or the initial speed here is of a slope 1 over t, and then just goes here and just meets this point here, right. So if I keep on going at the speed of 1 over t, I will hit this point exactly at t equal to tau, right, at this point, which is my time constant. Similarly, if I go, so here with the speed, it will be at t equal to 2, that I am hitting this value, right, like this and then this one. You can compute it, right, for different time constant. This is a general formula for that, and of course the slope keeps on decreasing and so on, right. So okay, why is this important, and then why can't I maintain this speed all the time and just go to 1 in 0.6 seconds than just going this way. Well, this phenomena essentially is because of the dynamics of the system, which gives you a response like this, right. Now these curves could be explained by what is in here. So this we could this is something what we also experience in our daily lives, right. If I take an elevator from say floor number 1 to floor number 6, you see that the initial velocity is a little higher, and then as it goes up and up, you do not have the same velocity all the time until you reach the 6th floor and then abruptly come to a stop. You keep on going up, and then the velocity keeps on growing down, and then you just stop at the 6th floor very gradually. The same even when I am driving a car from point A to point B, right. I build up a velocity and then I just do not go and hit that point and then stop abruptly, right. I just stop gradually. So this is a phenomenon that could be explained that kind of fashion, right. And then this, if you look at the slope also decreases monotonically as t goes to infinity and until it reaches slope of 0. Okay. Now what about these guys here? Then how would I say that I have actually reached some kind of a steady state value, right. I do not have to wait till infinity. So how do we define is, if I say of what, I will slowly define a term now called the settling time. Or when I would say that my system has actually reached the steady state is when I am within 2% of the final value. Right. So if I reach 0.98, like for example after 4 time constants, then I say that my system has actually reached a steady state. This will be very useful for analysis purpose, right, this definition of settling time, right. So okay, so after this, well, you can look at the unit ramp response. Okay, so even before I do this, right, so let me do something else also here, right. So here my reference was a unit step. If I just look at the standard configuration of the plant and controller, so I had, I think if I just remember correctly, it will be 1 over tau s. I had unit step here, which was my r of t, this, right. So y of t, a plus, a minus. So if I call this, say, the error signal, right, E of s, the difference between the reference and the output. Okay, so let me define something, right. So the error E of t as r of t minus y of t. Okay. So what is r of t is just a unit step 1, and what is y of t? Y of t is 1 minus e power minus t over tau. Okay. So this is simply e over minus t by tau. Again, this is all times greater than or equal to, say, just this 0 plus. Okay. Now what happens to error at infinity? right. As t goes to infinity, this is just my term, right, that it goes to 0, means at infinity. So, if E of infinity is 0, from this expression I can say that R at infinity is y at infinity, and so this is exactly what is happening here, right. At infinity both signals become the same, right, that my system, I can say, it asymptotically tracks a unit step, right. So, no matter what the value of the time constant is, this guy does a little slower, but it is here. You could have even slower guys which could do here, but they would eventually again go to the value 1. So, this system, I would say, again I am sorry defining these terms, but we will elaborate this a little later, has a steady state error of 0, right. I can just call this, okay, I am running out of space here, but let me write it here. So, how do I define this? There is a difference between the reference and the output, and how does it go at infinity. Okay. So, okay, now what happens when the input is a ramp, or when I am actually asking my system to track a ramp. Okay, 1 over tau s plus 1 r of s, and then I do all these things and I see do the inverse Laplace. So, the response to a ramp would look like this: t minus tau plus tau e power minus t over tau. Okay. Again, how do we classify or how do we differentiate between the transient response and the steady state response? Well, the transient response, well, the one which goes to 0 for very large times is this guy, and at steady state this guy still remains. Okay. So, it need not be so earlier we saw in the first example that the steady state was 0. In the second example, when I was tracking a step, the steady state was 1, and now we see it is actually depending on time also. Okay, we will see what these things actually mean. Okay, so let us see first what is the error, right. Does at t equal to infinity, are my responses just meeting the original signal or not, right. Again I just draw it for the sake of completeness here, that here I have r of t, I have 1 over tau s, a plus, a minus, and I have a y of s. So, sorry, y of t, or whatever notation we want to follow. Okay, okay, better y of s, because this is s, this also be s, capital R of s. Okay, so at infinity, does my output track the ramp, right? So that depends on what is the error signal here, E of s. Okay, so what is E of s or E of t? E of t is R of t, which is my t minus y of t. Y of t is the entire thing, t minus tau plus tau e power minus tau over t. Okay, so what I am left with is tau plus another tau e power minus t by tau. Okay. Now, if I do these things, E at infinity would be, well, this nothing will change here, tau plus this guy at infinity will go to 0. So, nothing will change here, tau plus 0 is tau. Okay. Now, what does this mean? So, this is my R of t, this is my reference signal, right. So, as t goes to infinity, I am not touching this guy, but I am actually just at a distance of tau, which is 1 in this case, right. Here I am just at a distance of 2, right. So, there is some kind of a steady state error here, which is just governed by this number tau. The smaller this number, smaller the steady state error. Okay. So, what I conclude is that, well, a first order system, if it has a ramp, it will have some steady state error. Okay. How do I encounter a steady state error? Let us say I just again take this example of a pendulum, right, and I started with some non-initial condition, and I expect it to go to theta equal to 0 if this is theta. But okay, but there could be something in the system which stops it going, maybe it just stops at theta equal to say 0.1 degrees, right. So, that is the idea of this steady state error. Right. So, it does not really reach the desired value, but some number very close to that. There is an error, but there is a way to determine that error, how small it is, how large it is, I can directly quantify by just looking at the dynamics of the system. Okay. Now, finally, we will see another test signal is the parabolic input. Well, R of t is t square over 2, the I know that the Laplace transform is 1 over s cube, and I do all these things and I get signal which is t square over 2 minus these terms plus tau square and so on. Okay. Again, this has a steady state, this transient term which will just die down as time goes to infinity, and a steady state term, well, which actually looks possibly quite worse, right, than the original one. It has a t square term now, right, it's no longer constant. Okay, what does the error do here, right? So, can my system track a unit parabola? Okay, so the error E of t is my reference signal, that is t square over 2 minus the output, that is t square over 2 minus tau t plus tau square. Okay, I would exclude this exponential term because I know it will not contribute to the steady state error, right, it will go to 0 anyway. So, this will be tau of t plus or with a minus tau square. So, E of infinity is actually a little strange here, right. E when t goes to infinity, this guy also goes to infinity. So, the error will be very large. So, if you see that the distance between these two, this is my actual reference signal and this is my y of t. As I go to infinity, this distance will keep on increasing, right. So, it will keep on increasing, and then if you keep plotting this forever, you will see that distance actually becomes unbounded. Similarly with here, with a different time constant of tau equal to 2, right. Okay, before this, right, so in one of my earlier slides, what I had shown was that these things, right, I take a parabola, I differentiate it, I get a ramp, I take a ramp, I differentiate and I get a step. Now, let us see if the responses also follow some kind of a pattern like that. Okay, so this is my response here, right. So, this is this entire thing, or this guy. Okay, so just let us differentiate this with time. So, d over dt of yt in this case would be t minus tau, and then here you will have plus e power minus t over tau, 1 over tau will be here, something like this. Okay. Now, okay, just remember this t minus tau plus tau e power minus t over tau, and this looks something like this, right, exactly this one, right. This is just the differentiation of dy by dt for a unit parabola. Okay. So, I differentiate the response, I get now the response to a unit ramp. Okay. So, the differentiation holds until now. Okay. Now, let me differentiate this again, dy by dt when the input is a ramp is okay, this will be 1, this will go to 0, this will be a minus e power minus t over tau. Okay. Now, okay, just see how this looks like, 1 minus e power minus t over tau. We'll go back slides and okay, oh, this is the same, right, this one. Okay, and I can keep doing this, right. So, you see that if the signals are preserved under differentiation in this way, that I differentiate a parabola to get a ramp, the responses are also follow the same pattern. If I know the response to a parabolic input, how do I find the response to a ramp? I just differentiate this. Again, from here to here, one more differentiation, here to here, one more differentiation. Okay. Okay, good. Now, we go to something slightly complicated, but still not very complicated, but very useful. So, second order systems, these are the systems which have two poles. Okay, we have done lots of examples on this. A typical RLC circuit would have a transfer function like this. If you remember vaguely, this was a transfer function between the voltage of the capacitor and the input voltage. Similarly, for the mass spring damper system, where I was taking the input was a force, output was a position or a velocity, one of those. And then, okay, in general, I can write transfer function as, well, a second order polynomial in the denominator and some number in the numerator, and I slowly will learn why these are equal, what are these numbers, and so on, right. Okay. So, the response here will be a little more tricky than what we saw earlier. Okay. So, how do I derive the system? Okay, let me start with an open loop thing which looks like this. I have a unity feedback and I go to a closed loop transfer function which looks like this. Okay, some terminology which will shortly be clear is that omega n is what I call as the natural frequency of the system. Zeta is the system damping ratio. Okay, let us just remember it with these names at the moment, and we will see slowly what they could mean. Okay. Just some properties of it. The damping ratio is a dimensionless quantity and it describes some kind of damped oscillation during the transient response of a system. Okay. So, this we will leave to the next lecture or the lecture after that. That is, it is a ratio of the actual damping to critical damping. No need to understand this statement at the moment, but we will recollect this when we go and then try to justify what this means. Natural frequency is the frequency at which the system tends to oscillate in absence of a damping force. Okay, this will be clear shortly, again together with omega d, which is the damped frequency of the system. Okay. So, we'll again come back to this as we learn it through some examples. Okay. So, the response is essentially now depending on the damping ratio zeta. Some classifications before we understand them physically is when zeta is greater than 1, I call my system to be overdamped. Zeta is 1, it is a critically damped. Zeta between 0 to 1, underdamped. Zeta equal to 0, undamped systems. You might have encountered these words somewhere earlier in some of the courses. If not, do not worry, we will try to define all those things. And of course, we are not really interested in negative damping at the moment, because again all the things we are doing are restricted to stable systems, but a system with a negative damping ratio could resemble a behavior of an unstable system, which we are not interested in at the moment. Okay, what is a damping, right? So, damping is something which kind of reduces or prevents oscillations in the systems, right. So, I could have systems which are overdamped in a way that transients exponentially decay without any oscillations. I would have critically damped where the systems decay to the steady state value with or in the shortest possible time. I could have oscillations which actually go to 0, and I could have undamped systems which just keep oscillating at its natural frequency without any decay in amplitude. Okay. So, a typical response, the red color here would be an undamped system. Okay. So, let me see if I could explain you with the simple pendulum example, right. So, I am here, this is my theta equal to 0 position, and say I have an initial condition starting at say theta equal to some 15 degrees, right, whatever, some other theta, right. I am starting here. If the system does not have, is not subject to any sort of friction either here or in the air. So, what we expect is it just keeps oscillating, right. So, you just go from theta equal to 15 degrees if this is a plus, if this is okay, let me call this minus 15, it will go to plus 15 and just keep on doing this, right. So, this will correspond to the behavior when zeta is 0, and I will explain you this mathematically very shortly. There could be cases when I could have a situation where this guy goes from 15, maybe it will go to a 14.9 here, come back, and it will keep on oscillating, go back and forth until it reaches this point. So, these are called underdamped systems, right, when zeta was less than 1. There could be a situation where I start from theta equal to 15, I go and I just slowly settle here, I do not go to the other side, I just go and I just stop here. Okay. There could be, say like this is some time, say in 1 second. There could be situations where I start from here again and I go very slowly, and say I am going in 3 seconds. There could be even worse situations. So, I am not going, I am not crossing this line. I am not crossing this line, okay, the Lakshman Rekha here, so you can call it. There could also be situations where I start at theta is again 15 or minus 15 depending on the convention, that I am going very slow, very slow, very slow, and I just stop here. This could take me 10 seconds. Okay. So, few kinds of responses. Zeta equal to 0, I keep on oscillating, right. For some value of zeta less than 1, I am oscillating, but my oscillations are dying down, dying out before I reach this steady state position. There could be situation where I just go from here till here in 1 second and just stop. I do not go beyond theta equal to 0. It could take 3 seconds, it could take 5 seconds. So, the fastest value of, and these things will vary with zeta, right, zeta equal to 0, zeta less than 1, and then all this behavior would be zeta greater than or equal to 1. So, the fastest where I can reach here and stay is the critically damped response, okay, which is like the blue line here. And for damping anything larger than that, I will just keep taking a longer time. I could have a response also here, right, something like here, which could be say for zeta still greater than 1. Right. So, these are typically the 4 kinds of responses which we will encounter in designing a system. If I take, for example, I want to design a lift or an elevator, and I want to go from, say, this is level 1 to say level 2. I am lazy and I do not want to walk, and I take this elevator and I go up. I do not want my system to go to 2 point, halfway to the 3rd floor, come back here and then do this, and I do not want it to do this, right. No, that will be very unpleasant, right. Even if, like you see on TV, even if Deepika Padukone is stuck with me, this will still be very unpleasant. And therefore, what we design these systems are to be critically damped or like slightly over damped, right, that I just go here and I just slowly settle down here, right. So, again depending on my requirement, I would just want to have my system to be either be under damped, critically damped, or even sometimes over damped. Okay, we will characterize all this very shortly. Okay, so how does my system behave again with the standard test signals? So, here I have to be careful that there is another thing, just not just a test signal, but something depends also on the value of zeta, right. So, earlier my formulas were very easy to remember, but here the zeta adds more complexity to me, right, or more, it presents me with more test cases. So, y of s is omega n square, s square plus 2 zeta omega n s plus omega n square. Okay. So, zeta equal to 0 would be this guy would go away, y of s is this one, and I can do the inverse Laplace, and I can just say that I just have a sinusoid of some frequency omega n. Okay. Let us highlight this very nicely, omega n. Okay. How does the response look like? Well, the response is just a sinusoid. I say, what is its amplitude? Well, amplitude is this one, it could, okay. Now, what I am interested is the frequency, okay. Zeta is 0, and if there is no damping, it will oscillate at omega n, okay, and therefore, I call this as the natural frequency as defined earlier, right. So, here, so where did we define that? Yeah, this the system natural frequency, the angular frequency at which the system tends to oscillate in the absence of damping force. That is exactly what we did now. There is no damping force, zeta disappears, and then naturally my system just oscillates. Okay. So, this is the natural frequency when there is no damping. Okay. So, let us make things a little complicated. Okay. So, sigma between 0 and 1. Okay. So, before I do this, I will just do some very short calculation here. So, look at the denominator, I have s square plus 2 zeta omega n s plus omega n square. Okay. So, just to say, if I look at how do I find the roots of this, these roots would be, okay, so minus zeta omega n plus minus square root of zeta omega n square minus omega n square. Right. So, this is how this roots will look like, divide by 2, and you saw the standard formula, or this is minus zeta omega n plus minus omega n square root of zeta square minus 1. Okay. Now, when zeta is less than 1 and of course greater than 0, this will become a complex number, right, and therefore the roots will look something like this, let us say here, and I call this guy, okay, so if it is complex, I will just, okay, I will just write it here, minus zeta omega n plus minus j omega n square root of 1 minus zeta square, and this guy I will call as omega d. Okay. So, and that is how this roots now expand, right. It's s plus zeta omega n minus j omega d and plus j omega d, exactly what is here. Okay. Now, I just want to see the natural response or the impulse response, and I see, okay, I just do all the Laplace transforms, inverse Laplace transforms which I learned earlier. I see that y of t is some number here, omega n blah blah blah. Then I have an exponentially decaying term and this guy. I say exponentially decaying because all these guys are positive, and with time, it just falls in value and goes to 0. Okay, it is still now earlier. Here I had sine omega n t, whereas here now I still have a sine curve or a sine wave, but with a different frequency, that is omega d, right, and therefore I call this as the damped frequency, the system damped frequency, angular frequency at which the system tends to oscillate in the presence of a damping force, right, where zeta was greater than 0, but less than 1, and this is exactly the formula we use there. And this omega d is not because of any magic that I define, it just because it just sits in beautifully here in the term of sine omega dt, right. This is why I call this omega dt as the damped natural frequency. This is omega n square root of 1 minus zeta square. Okay. So, this is the damped frequency, and of course, I have this exponentially decaying term, and if you see the response, well, it will keep oscillating and eventually go to 0. That is the response of the pendulum which we had talked about, right, when zeta was greater than 0, but less than 1, right. And the sign here says that, well, there will actually be oscillations, right. I will just go to whatever this number here is, come back, and of course, these numbers then depend on what are the specific values of zeta and omega n. Right. Okay. Now, other case could be when zeta is 1. So, when zeta is 1, my expression for y just looks like this, s square plus 2 omega n s plus omega n square, and the inverse Laplace would just be like this. Right. And if you see the sinusoidal term has disappeared, which means there will not be any oscillations. However, you will see that as time goes to infinity, I just come back to 0. Okay. This is again for a particular value of zeta equal to 1 and omega n. We will later investigate what happens for larger values of zeta and so on. Right. So, this is, so here for a system which we actually call now as a critically damped system. The transients in the system decay to a steady state without any oscillations and in the shortest time possible, right, as we had defined in the case of the pendulum. Here this is the shortest time, and this is the critically damped case. Okay. Now, I could go to overdamped system where this zeta is greater than 1, in which case these roots will just be real, right. So, zeta less than 1 I had complex roots, but I will just have real roots. Okay. So, what happens here? So, omega n square plus s square to zeta omega n s omega n square, I can just write it as a composition of 2 real roots like this, for which the response looks like 2 exponentially decaying signals, right, zeta omega n blah 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 and zeta omega n blah blah blah. And again, this response you could see there is no oscillating term here, right? There is no sinusoidal term. So, you just go here and then just come back. Possibly when zeta equal to 3, you might have even much slower response, like it could take even much larger time like this and so on, right. So, we saw 3 cases now, right. First is actually 4 cases. The undamped case, where I have the system just oscillates at the natural frequency. Then I had oscillations, but they just die down. They die down because of this exponentially decaying term here, right. and they still oscillate at now a new frequency which is which my zeta defines. Again you can just put zeta equal to 0 and say it will again go back to the damped natural frequency. Okay, and then a critically damped system and what we call as an over damped system. Okay. Now this was all about the impulse response. Now how will these guys behave when there is a step response? Okay, so step is my R of S is 1 over S and then Y of S would be something like this, right. So I just have a S over here and blah blah blah. Okay, case of zeta equal to 0. Undamped system, well, nothing should change in principle as what was observed from the case when I had just an impulse response. So Y of S, I just do all the math and I see, well, Y of t is 1 minus cos omega n t. Okay. So this system, well, it's just 1 minus cos omega n t, it will just be like this. Right. And you can ask me, sir, what is a transient and steady state? Well, this guy will never reach a steady state. Right. Whereas, okay, these guys here, these guys will have this kind of transient terms which go to 0. Even the previous guy would have a transient term which goes to 0. And you see that the steady state is again again coming back to 0. Correct. Here also you will have the transient term which actually is going to 0. This entire term could be viewed as a transient term and the steady state term is again 0. Here, well, there is nothing like that, right. There is nothing which is actually vanishing with time. So there is no, possibly we cannot nicely classify what is a transient and what is a steady state. Its transient behavior is actually its steady state behavior and it will never converge to any fixed value like a 0 or a 1 like in the previous case. Okay. So same thing happens when I have a unit step response. I am still doing this one, right. None of the term actually disappears as time goes to infinity. All terms are just intact. Okay, this is again zeta equal to 0, omega n equal to 5 and the reference being a step. Okay. Now we will do all the same cases which we did earlier. I will just skip all the math here, but we will see how my final expression looks like, right. So for zeta equal to this guy, I will start with this and then have this one and I will of course have complex roots and all this will be taken care of here. So my response has 1 minus some exponentially decaying term. Again you have some oscillating terms here which could be further simplified to look something like this, that is 1 minus e power all these exponentially decaying terms and this one, or I could call this as my transient response and this as my steady state response, right. And okay, where theta is, will at the moment we will just say that, well, the theta comes as cos inverse this zeta. Of course, we will not really worry about what this means, but all the math would tell me is just this one, right. Okay. So how does the response look like? Y of t goes, so I want to track this number 1 and I go up and overshoot and then I go below 1 and then I eventually go to this number. Okay. Which I can directly say here now, I do not really need to compute what is the steady state error. Just by looking at this thing, I can say that the steady state error at infinity is just 0. We will do more analysis on this, but just as a passing observation, I am just introducing you to these terms at the moment, right. Okay. And of course, we can have different behaviors for different zeta, right. As zeta is, so intuitively you can see that as zeta goes to 0, is very, say zeta is very close to 0, say 0.01, then you could actually expect a response which is like this. When zeta is very close to 0, you could expect a response like this, but which is very slowly decaying, right. So it might actually take a very long time to decay. So I can just draw something here. Be here, here, and I will see these oscillations for a very long time, but they will slowly die down, right. And of course, as zeta goes to very close to 1, then you will see that the oscillations are also minimal. Again, this omega d guy just sits here, right, the damped frequency of the system, and this is again because of this guy, the zeta, right. The justification to why we introduced this term specifically and called it the damped frequency of the system, because this is the frequency of the signal when there is in the presence of damping. Okay. So next, what happens when I am critically damped? Okay, I will just skip all this math and just see that, well, the sinusoidal terms disappear and I have just this one. yt is 1 minus e power blah 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 blah, right. And I can just compute this response either with the final value theorem here, or just put the t equal to infinity and I can just compute the error, right. The error is again 0. So, this is like it goes from 0 to 1 in the shortest possible time and just stays there, right. Okay. The next one is the case of an overdamped system. Again, we will have two exponentially decaying terms, which well it will just be like this, right. So, it will go a little slower than the previous one, and you could just plot things where if zeta goes to 3, then possibly you will have a much lower response, zeta equal to 4 and much lower response. And the limiting case we will say, well, there is a very large zeta, then you just refuse to move, right. So, these are also in literature referred to as very sluggish systems, which are like very slow to respond, right. Okay. So, also in this case you can just naturally see that the steady state error goes to 0. Okay. So, what we have learned so far today is what do we do with the models which we obtained from our previous classes. So, once I have the models, I need to subject them to some real time conditions, which I possibly would not be able to emulate when I just have a system at hand. So, I will just give it a certain test signals which will be closer to what I can see in reality, and therefore, I have a series of signals. In my case, I have the impulse, the step, the ramp and a parabolic kind of signal, and we just saw how we could define what we call as the settling time, what are the transients, what are the steady state, and we did it for the first order. Second order case was a little more interesting because the damping actually played a role in the dynamics of the system. If I have oscillations, if I have sustained oscillations, if I have decaying oscillations, or if I have no oscillations at all, right. Okay. So, that was a summary of what we did today, and we will do a little more analysis, or we will elaborate more on this in the next lecture when we do more analysis on these time domain specifications. Thank you.